Good morning, class. I hope I'm planning to wait a little bit longer, maybe a few more minutes, uh, because right now I see there's only half the class here, so I'll just wait a minute maybe. And while we wait, there are any things that questions or something that people want to ask, we can get started. Actually, why don't we just start with the class because we can't. We do have a um, we do have to stop at some point. So. Uh, Regarding homeworks, these are all announcements that are available on Canvas. I just wanted to remind you, the homework is due on Thursday. This is about decision trees, and because a lot of you have been having issues with power and outages and internet and stuff, and um, I hear that some people had outages all the way till Saturday or Sunday. We'll be a little more relaxed with the late policy. So if you have issues submitting on Thursday, try to make it in by Friday. Some of you had asked if we could provide the data set in the CSV format in addition to the libsvm format. And so we have that. And we'll be doing that for future homeworks also. In these two formats are identical in terms of the information they contain. They're just different ways of writing down features and labels. And you are free to use either one, whichever one you want to. They are equivalent. If you've already implemented your libsvm reader, stick with it. It's a little bit more efficient, the libsvm format, in that it allows for sparse features. But given the size of the data sets that we'll be looking at in the class, it's not going to matter so much. There's a lot of discussion about the homework on Canvas, a lot of very interesting uh, conversations going on. Please take a look at it. Your questions might already be answered there. And if not, feel free to ask a question. We'll get to it. And either one of us or one of someone else in the class will answer the question. There's also a project milestone that's coming up, but I'm still in the process of cleaning up the data because I had a certain data set in mind, but it is not exactly how I expected it to be. So I'm cleaning it up, and you should hopefully my plan is by Thursday you should have the information about the project so that you can do something next week. Are there any questions about homework, projects, logistics in class in general? Feel free to use the chat.
I have a question. I just wanted to verify that we can use pandas in NumPy.
Yes, you can use pandas and NumPy. As far as I'm concerned, these are not machine learning libraries. These are just data support libraries. So you feel free to use them. Yes.
Great, thank you.
The restriction involves using libraries like scikit-learn or TensorFlow or PyTorch, which are essentially just machine learning libraries. Feel free to use any data manipulation libraries. The one catch is you need to make sure that it is available on CADE. I think it is. I think pandas and NumPy are available on CADE, but don't take my word for it. Just verify it on your own. Are there any other questions? Is there a penalty if we submit on Friday? So as I said, I'm not going to have a penalty. It's just for this homework alone because of all these technical issues that we've been facing as a city. I'm not going to enforce the late penalty for this homework alone. So do feel free to submit on Friday. The official deadline is still Thursday because we don't want to have another late day after Friday. We can keep going. So the submission window will close on Friday, and we will not enforce the late penalty this time around. Some of you have already submitted. Feel free to submit early. You don't have to wait till the deadline. Another question is, should the code be run on Linux in CAD, or is Windows okay? Windows is totally fine. I think as far, yeah, Windows is also fine. Yeah. And and one other thing that I wanted to mention is, if you feel like you're spending a lot of time on the code and you're getting unhappy about it, let me make you a little bit happier. Any code that you write now might end up being used in future homeworks or maybe even your project. That way, if you do architect your code carefully and make it so that it's the things are not hard coded and so on, you'd be able to easily use it. Your project will get easier essentially. So the plan is, as the semester goes along, by the end of the semester, you'd have implemented your own very little machine learning library. You'll have like maybe 6 or 7 different learning algorithms in your own code base, and you can use any or all of them in your project. So the first homework is the one that takes more effort, simply because you're getting things set up, but this will pay off in the future homeworks and in the project. I don't see any more questions, so I'm going to get started with today's lecture. Today, I want to spend time on a little bit of a what might seem like a logistical thing, but is actually very useful and an important empirical point, which is cross-validation. So the plan for today is we'll spend maybe 10 to 15 minutes on cross-validation. You're already implementing cross-validation in your homework, and you'll be doing this for future homeworks also, and for when you use machine learning in the real world. And it's an important idea that should be part of your experimental framework, no matter what you do. So very at a high level, cross-validation is one of the many ideas that come under this notion of model selection. And the broad question is, how do I choose the best model given some data? This is essentially the general question of machine learning. We want to choose the best classifier or the best model for the data. Now, we should think about what are all these things that goes into defining a model. We need to know what the features are. And in your homework, I've already told you what the features are. So you don't have to, you don't get to make that choice. Sometimes you have to invent your own features. And I'm hoping that at least in one of your homeworks in the future, you will do some feature engineering just to kind of understand, get a sense of what goes into that. And then there are hyperparameters. Hyperparameters are all these things that there are some hyperparameters that can control the hypothesis space. For example, the depth of the decision tree in your homework is a hyperparameter that controls the hypothesis space. If you say that the depth should be less than 6 or less than 17, you are restricting yourself to trees that are within that set. So you're controlling the hypothesis space using some hyperparameter. We'll see many other hyperparameters that also control the hypothesis space. When we come to, for example, neural networks, we'll talk about neural network architectures, and that's a hyperparameter. Sometimes the learning algorithm itself may have hyperparameters. There may be certain hyperparameters that control how the learning algorithm executes. And we'll see some examples of this when we talk about gradient-based learning. And finally, there's the actual model. In the decision tree case, the model is the tree. So if you choose the right features, and if you choose the right hyperparameters for the hypothesis space, in this case, the depth, if you choose the right hyperparameters for the learning algorithm, for example, do you use entropy, or do you use the Gini index, or do you use the, what do you call it, the majority error and such things? These essentially change, they don't change the hypothesis space, they only change the learning algorithm. They change how the hypothesis space is explored. And then once you have those, you run your code and you get a tree. All of these together define the model. For the most part, in this class, when we say learning algorithm, we only talk about this last thing, only the, uh, and the learning algorithm will produce the model. So the question is, how do we pick the right features, and how do we choose the hyperparameters? How do we choose the hypothesis space? How do we control for all of these? Because if we choose the right things there, the learning becomes easy. If we choose the wrong things there, learning could be impossible. So it almost seems like this is a crucial component, and all of this fits into this notion of model selection. There are many different model selection strategies out there, and if you're interested, I recommend this book, Elements of Statistical Learning Theory. It's available online. You can find it, just search for the name. Chapter 7 talks about model selection strategies, and you will see ideas like minimum description length. We will talk in great depth about risk minimization, which leads to learning protocols there. Today we're going to talk about cross-validation. There are Bayes factors, AIC and BIC, which are, the IC is information criterion, and A and B are different names for these specific criteria. And there are many other model selection strategies. I think the most easy to implement and easy to explain one is cross-validation, and this is widely used across machine learning. So let's look at cross-validation. So the setting is, we want to train a classifier using a certain data set, but we need to know which features and hyperparameters we should use. If you give me the features and if you give me a set of hyperparameters, the learning algorithm does what it does. So your ID3, for example, will find you a tree if the right depth and the right features are known. But how do you know the best feature set and the best hyperparameters? And for example, the best in the case of in your homework, how do you know whether you should use the entropy-based criterion or the Gini index-based criterion? And the answer is, one of the answers is cross-validation, and cross-validation is a statistically robust approach. And I'm going to just describe the process in almost a mechanical way, just to kind of give you a sense of what you implement. So suppose you're given a certain feature set and a certain hyperparameter. Together, we are going to call this all setting. And the question is, how good is this setting for this data set? And remember, the goal is always, the way to identify how good a setting is we care about generalization. We care about future performance. We care about the test set, but we are not allowed to use the test set. So the question is, how do we know whether a setting is good or not without actually looking at the test set? So can we simulate the test set in any way? And the answer is the following. So let's say we are given a data set. This rectangle here represents, let's say, represents the data set. We split it into k parts. Let's say we split it into 5 parts. So each part is called a fold. So we get 5-fold cross-validation. Here in this picture, I've split it into 5 parts. What you do is you take 4 of these parts. By the way, this split should be random. This is important. The split should be random. And you also want to make sure that all labels are roughly equally represented in each split as it is in the full data set. So now what you do is you pretend that your full training set was not really all these 5 parts, but only 4 of these parts. And you set aside the 5th part and call it the validation set. So you run your classifier, you train your model using the feature set you care about, using the hyperparameters you want to evaluate. You train a model on these 4 parts, and you evaluate on this 5th part, which is called the validation part or the validation fold. If you do that, when you evaluate, you get some accuracy, right? Let's call that accuracy 5. It doesn't have to be accuracy. It could be some other metric that you care about. For this purpose of the slide, I'm just going to use the accuracy to represent that metric. So you get an accuracy. Let's call that accuracy 5 to represent the fact that it is accuracy on the 5th part, 5th fold. But what makes the 5th part special? We could do the same thing where we train on part 1, 2, 3, and 5, and test on 4, and we get accuracy 4. We can train on 1, 2, 4, and 5, and we get accuracy 3. 1, 2, 1, 3, 4, and 5, we get 2, and 2, 3, 4, 5, we get accuracy 1. So what we do, this is, if you think about it, this is such a mechanical process. There is nothing intelligent happening here. You split the data into 5 parts randomly. In your homework, we've already done the split for you. And you train on 4 and test on the 5th one, and you just essentially change which part gets evaluated on. What is interesting here is now you've got 5 different accuracies. You've got 5 different accuracies, and each of these, if your split is random, each of this is on an unseen part. Each accuracy is on a section of the data that the learning algorithm didn't get to see. So just to kind of very briefly revisit this whole thing, we split the data into k parts. It could be 5, it could be 10. In general, it's k-fold cross-validation. And then you train on the, I'm assuming here that k equals 5. You train your classifier on 4 parts and evaluate on the 5th one, the validation part, the validation set, and you iteratively go through each portion, each fold as the validation set, and that way you get, in this case, 5 different accuracies. And now you get 5 different accuracies, and in each case, the accuracy is on a set of data that the learner did not get to see. Now you take the average of these 5, and this average together becomes the cross-validation performance. So essentially, this average is a measure of how good the classifier is on unseen data. And because it's averaged across multiple different portions of the data, it is actually a statistically robust measure. Now, remember, this was for only one feature set and one parameter. We can repeat this for every feature set and every hyperparameter choice, and we get a ranked list for feature sets and hyperparameters. Once we have that, we know for every feature set, for every setting, we have a number, the performance number, the average cross-validation accuracy. For every setting, we have an average cross-validation accuracy, and we can now rank different settings by their average cross-validation performance. Now we have the best setting. Namely, we have found the best feature set, the best hyperparameters, and we believe this is good because across these entire things, a set of things that we've tried, this is the best one. Once we have that, this is our ranking criterion. This is the answer to the question. We evaluate every single feature set using cross-validation, and you pick the best one according to the cross-validation performance. And now you have a single feature set and a single hyperparameter selection setting that you believe is the best according to the cross-validation performance. And you go back to the full data and you train your classifier or you train your model on the full data using this one setting. And that's the setting that you want to sell. That's the setting that you believe is going to be robust in the future. If you want to deploy a model, that's the setting that the model that's trained with that setting is the one that you'll use. In some sense, this is a very naive idea because it's just, it may seem like brute forcing because you're trying out every possible feature set and every possible hyperparameter. But the important thing is that by averaging across multiple different validation sets, that's why it's called cross validation. By averaging across multiple different validation sets, you get a statistically meaningful estimate of future performance of this particular setting. And that's the setting that you'll use. Of course, it's computationally expensive because you have to try out, think about what you're doing here. For every feature set or every hyperparameter that you want to compare, usually we tend to not think too much about the feature sets. Let's just say every setting. For every setting you want to evaluate, you split the data into 5 parts and you train on 4 parts and you test on the 5th one, and you do this for every case. Of course, it's computationally expensive. That's the bad news. But the good news is this is ridiculously trivially parallelizable. Because remember, in this picture, every thing here is independent of every other thing. Every fold, every accuracy calculation is independent of all other accuracies. And this is even within one setting. Every setting is independent of all other settings. So you can run this on multiple machines. You can run this on multiple cores. And this is parallelizable to the extreme. And so you can do that. That way, the answer is you try to find as many computers as you can find, run cross-validation on all of them by setting things up so that every fold of every setting runs on a new machine or a new thread, and you aggregate the results. And this is why training and hyperparameter selection can take days, if not weeks. And I've heard of at least one instance where hyperparameter selection took months because they tried everything that they could think about. And machine learning today is an empirical field. We'll see a lot of theory, we'll see a lot of math and all that stuff, but this, what I just described here, makes machine learning an incredibly empirical field, because given just a data set, if I just throw a data set at you, you may not know which feature set or which hyperparameter is the right thing. So we will have to do the the rounds of all possible trials. So there is a question, which is an important question. Does testing every hyperparameter increase the risk of overfitting to the training set? It does. And this is where we have to walk the tightrope. We may end up overfitting that. So if we are doing cross-validation across every single hyperparameter there is, and every single feature set, we will end up overfitting because we are overfitting because we are trying hard to find the one setting that gets you high cross-validation accuracy. There is that risk, but at least on the good news is, even though we are, it's a perverse kind of overfitting, because even though we are overfitting the training set as such, at no point is the classifier that we are evaluating looking at the validation set, because the model is trained only on, is always evaluated on unseen data. So if your folds, if your parts are big enough, each part is big enough, you do still get a robust estimate of future performance. But one way to see if you're overfitting is you can look at the variance of these accuracies. If the accuracy between, if the variance is high, that is, accuracy 5 is very different from accuracy 3, and accuracy 3 and 5 are very different from 4, that suggests that you have very little data, and you probably should not trust the cross-validation results. But this is one of the reasons why, in general, I would not advise you to try everything you can think about and throw it into cross-validation. You spend some time thinking about the data, and you have a small set of features that you care about, and you understand the insights of the learning algorithm. You know which hyperparameters are meaningful, and you don't try out everything and hope that you accidentally find a statistically meaningful but actually meaningless model that just seems to fit the data. There is another question. I assume running our cross-validation sequentially in the homework isn't going to cause any issues. Most likely not. The data sets that you encounter in your homeworks are small enough that it should not cause issues. But if you want to parallelize things in your code and just to see what the difference is, if you want a challenge, I encourage you to try to parallelize it and see if you get the same results. You should not face too many issues with cross-validation in your homeworks. And if you do, tell us and we'll try to work around. We'll find a workaround. There's a possibility that for your project, you may want to do some sort of cross-validation in parallel, but this is one of the things that I'm trying to figure out to see if you don't have to deal with that too much. One of the ways in which you get around this sort of heavy computation issues is to drop the cross part of cross-validation. You split your training data into a training and a validation set. Essentially, just keep one of these folds and evaluate every hyperparameter on that. Of course, there you lose the robustness because you don't get the multiple accuracies. There's another question. If we have multiple hyperparameters, would we need to try combinations of them, or are their impacts on accuracy independent? That's a very, very good question. So let me restate the question. Suppose you have a learning algorithm where you have two hyperparameters. Let's call that hyperparameter alpha and beta. That, we will encounter learning algorithms that have many hyperparameters. Let's just take two. Let's say alpha can be 3 things and beta can be 5 things. And the question is now, can you fix the alpha independently of the beta and just do cross validation on each one of them independent of the other? Or do you have to try the cross product of all of them where you have 15 possible combinations? The sad answer is they can interact with each other. Sadly, you have to try all combinations, which is really an annoying thing, because if you have two hyperparameters, 15 seems like a manageable thing. If you have 10 hyperparameters and each one of them takes 10 values, suddenly it seems like it's too much. The answer there is now, again, you think about which hyperparameters are important. Some learning algorithms tend to be very sensitive to some learning hyperparameters, or some hyperparameter choices tend to be sensitive and some don't tend to be sensitive. And if you understand what the learning algorithm is actually doing, you can choose the insensitive, the hyperparameters, the one that don't change the result too much. You can choose them independently and then just freeze those and just do cross validation, do a cross product of the ones that are sensitive. So I'm not going to, we haven't yet encountered enough learning algorithms for this to make sense, but as we go along, hopefully we'll see a few that where this comes up. Is there a way to prune instead of eliminating? I don't know what cross is. So is there a way to prune hyperparameters instead of eliminating? And this is essentially what I described. If you believe that a certain hyperparameter is not very important, you need to pick a number, but you don't need to spend like every possible combination. Then you can essentially pick a number. Let's say there is a hyperparameter alpha that can be either 0.1, 0.01, or maybe, actually, let's say alpha is 1/8, 1/4, half, or 1. It has to be one of these things. But somehow, because you know how the learning algorithm functions, let's say you believe that alpha is not going to interact with other hyperparameters. So what you do is you freeze all the hyperparameters, pick one of them. Let's say 1/8 is the best. You pick 1/8, and now you freeze alpha equals 1/8, and you just do cross validation for the others. So this was the question of whether you can do this independently or not. If you know, because you understand how the algorithm works, if you know that alpha is independent of all the others, you just pick it independently and you prune the hyperparameter space. And in some sense, in production systems and in machine learning in the wild, there will be many hyperparameters, and it's a pointless exercise to try to do cross validation across all of them. So you will have to choose, freeze certain hyperparameters and then pick the rest. One very immediate thought that comes to mind, and I see that's also the question that's in the chat, is it almost seems like choosing the right hyperparameters itself is a learning algorithm. Can we use a learning algorithm to find the hyperparameters? This is a dangerous path, because what happens is if you do that, you will overfit. You will overfit the training set, and it tends to, you may find hyperparameters that look good on your test set, but they may look good with cross-valid. You may fool yourself into thinking that your learning algorithm is doing something good. Doesn't mean that you will get a bad classifier. You may end up accidentally finding a good classifier, but treating hyperparameter selection as learning tends to lead to overfitting. There are some cases where this works, but it's a dangerous It's something to be careful about. All right. This is pretty much all I have to say about cross-validation. You're implementing cross-validation for your homework. You'll be implementing cross-validation for all your homeworks. So you may want to think about, you maybe not for this one, but you may want to think about how to implement it in a way that works irrespective of which learning algorithm we use. Again, this goes into this idea that you think of yourself as building a machine learning library. All right. So there was another question. Where are these slides, the cross-validation slides on the class website? You'll find them in the model selection page, and I'll post a link on Canvas after we are done. Okay, so we're going to now go back from experimental stuff back into something more conceptual. We're going to spend a fair amount of time in starting today, going ahead for a few weeks now, talking about linear models. A lot of work in machine learning was developed using linear models, and linear models are convenient because they lend themselves to interpretation, they lend themselves to easy understanding and algorithm development. And when we encounter algorithms with linear models, they come with guarantees, and they are extremely well studied. So we'll spend a fair amount of time looking at linear models with the understanding that a lot of intuitions that we build with linear models translate to when we generalize beyond. So let's get started. But before that, let's see where we are in the context of the class. We've looked at supervised learning. We've seen what instances are, what concepts are, and hypotheses. Hypotheses and essentially, machine learning is search over a hypothesis space to try to find a certain concept or a target function. And all these functions take instances and predict a label. In the supervised setting, we have labeled data that gets thrown into a learning algorithm to produce a hypothesis. More recently, the word hypothesis is almost is more rare to find, and people use the word model. These two are equivalent. So the labeled data goes into the learning algorithm, of course, with hyperparameters and all that, and you get a model. Now, when a new example comes in, the model is a function that takes examples and makes a prediction. We've seen only one specific learning algorithm so far, which is the learning algorithm for decision trees, which is the ID3 algorithm, and some variants of it. But we've already encountered a few general machine learning ideas. We have seen this concept of using features as high-dimensional vectors, and we will expand on this idea as we go along. We've also seen this important notion of overfitting. Overfitting is the idea where your learning algorithm produces a model that does better on the training set than it generalizes. So it essentially memorizes the training set. So this is the difference between memorization and generalization. Overfitting is memorizing the training set and not doing well in the future. Before we jump out into linear models, are there any questions about this big picture? Seems that there aren't. So let's move to linear models. So we're going to look at linear models, and which is a new hypothesis space. And anytime you encounter a new hypothesis space, we need to know a few things. We need to know what they are, namely functionally what they are. What do they look like in math? Formally what they are. And it's worth thinking about what kinds of functions they characterize. So we'll look at what linear models are, both for regression and classification, and we'll spend a fair amount of time on linear classification. So we'll look at what kinds of functions linear classifiers can express. To introduce linear classifiers, let me first start off by saying, talking about why it's worth looking at linear classifiers and linear regressors. Um, and here I'll call upon an Occam's razor or simplicity kind of an argument. And then I'll talk about the geometry of linear classifiers. Linear classifiers have a nice geometric interpretation. And then I'll spend a little bit of time on something that is tedious, but it will simplify life going ahead because we will have fewer bugs, both in math and code. And so I'll spend a little bit of time on this notational simplification. And finally, talk about how we'll go ahead with learning these linear classifiers. Of course, we will encounter many different algorithms for learning linear classifiers. So let's get started. I want to go back to this point that we saw in the first week of the lecture, that it almost seems like learning is impossible. If you are given a data set is just a small slice of a large function. You're given only, in this case, only 7 rows, and there are 2 power 16 possible functions, because how do you define a function? This column defines the function. It's essentially, there are 16 rows in this truth table, and there are 16 positions where we can either put a 0 or a 1, which means there are 2 power 16 possible functions. Every way in which you get fill up that column gives you a different function. We've only seen 7 of these positions filled. And without knowing what the rest of these positions are, an adversary could fill up these other things in any way it wants. So in some sense, learning seems like it's an impossible thing, because if nature is adversarial, it can fill up these question marks arbitrarily. Nature can, if nature has a free hand, it can do whatever it wants. How could we possibly learn anything? And the answer was, we essentially make an assumption. We make an assumption that nature does not have a free hand. Nature cannot pick functions to fill these slots in arbitrary ways. It can only choose functions from a special class of functions. In some sense, we make an assumption that nature has some sort of a regularity in it. And if we can find this function space that nature is choosing from, our search space gets reduced. And as a result, if we find a function within the small search space that fits the data, it's probably not coincidence. So now the first question becomes, how do we find this hypothesis space? How do we find the set of possible functions that our learning algorithm is going to explore? There are many different hypothesis space. One class of functions that you are exploring in your homework is a set of decision trees with a limited depth. We are restricting the search space. Linear functions are just another hypothesis space. So we will look at linear functions as from this point of view. It's another hypothesis space which restricts the hand of nature. So let's see how this works. So let's say you're given these points so you're given these points on the 2-dimensional plane on your screen. There are some points which are circles, the blue circles, and there are some points which are the red triangles. And the goal is to separate the blue circles from the red triangles. And let's say we have 2 possible options. We can have a curve, this curve A, which perfectly separates all the points. And then there is this other thing, that's the line, there's a line B, which makes mistakes. It puts this triangle on the wrong side, it puts this circle on the wrong side, and this triangle on the wrong side, whereas the curve A gets all of them right. So the question for you to think about, by the way, in all cases, the left side is blue and the right side is red. So now the question is, which of these is better? At this point, if I didn't have technical issues, I would be launching a poll, but unfortunately, I can't right now. So let me, you can post a message on the chat. If you have to pick either curve A or line B, which of these is better? And there's a question, is the data noisy? we always assume that there's noise in the data. We can never be guaranteed that there is no noise. And many of you are saying B, and one of the annoyances about not having a poll is that okay, there's one person who says A. I was going to invite someone who says A to justify it. So can someone try to justify why A might work? I mean, many of you have said B, and for a lot of reasons. So why might A be better? Assume that the data does not depend on anything but these two coordinate axes. And I'm not going to use X and Y because X is Y is usually reserved for the label. So let's call this X1 and X2. So the one possible answer for A is that A has more accuracy. It seems like A has perfect accuracy on the training set. So on the trade-off between simplicity versus accuracy, let's say that A is defined to be a polynomial of high degree. So let's say we have a 15th degree polynomial. So on the axis of simplicity versus accuracy, A has higher training accuracy and B is more simple. Now, the question is, we don't care about training accuracy. We don't care about training accuracy because we already know the labels for all the training examples. If you give me only training examples, I can give you a perfect classifier. If you give me this triangle, I'll say it's, if you give me this point, I'll say it's a red triangle. If you give me this point, I'll say it's a blue circle, and this point also a blue circle, because I already know the labels. The point to think about is not any of the data points that we already have, but a future point. Let's say a point here. Let me use a different color. This point here, the X that I have marked on the slide. That point there could either be a blue circle or a red triangle, but the curve classifies it as a circle and the line classifies it as a triangle. Now, I don't know about you, but this is where it becomes an intuitive argument for now. Personally, I would say that point should be a red triangle because the curve might be fitting the noise in the data. Getting 100% training accuracy in the world of noise requires not just fitting the signal, but also the noise. And in general, models that are more complex have this room, have the capacity. This is the word I'll use a lot, model capacity. And for now, I just want you to kind of think of this as an intuitive idea. We'll formalize this later. Complex models have the capacity to represent not just the signal, but also the noise. Think about this point that I have marked here, this X here, anything in this region. We don't know. We have no information from the training set about whether that region should be a triangle or a circle. But because we are choosing a model with a higher capacity, it has decided that that region is a circle. We can't tell for sure. And this is where we have to pick a model that introduces some sort of an inductive bias. And a common inductive bias is the following. Simpler models don't have the capacity to fit the noise. So what we would like is the simplest model that fits the data, but does not have the capacity to fit the noise. And as a result, we tend to start thinking about smaller models, less simple, less complex models. And one of the most simple models that we can think about are linear models, essentially a line that separates out one class from the other. Same argument also applies for regression. If you have these kinds of points and we need to draw, in this case, we want to find this function f for a point, for each point, for this thing here, we want this something like that. We can have a curve that perfectly goes through every point, including potentially the noise in the data, or we have a line that in some sense takes the average. And the preference for the line comes from the fact that we believe that the curve might end up fitting the noise. it's entirely possible that there is a phenomenon in nature that justifies the complexity of line A, of the curve A, but you need to justify it. You can't just fit the data. Um, there are a few comments in the chat. So one of the comments is that we are intentionally crippling the model capacity in order to stop it from fitting the noise. Is there a way to keep the capacity and stop it from fitting the noise? And the answer is, this is the sweet spot that we hope to get. We want to find the most capable model, but one that is capable enough to fit the signal, but is nothing more than that. And this is something that is a hyperparameter, if you want me to be casual about it. It's a hyperparameter choice. How do we know? It's essentially a hypothesis space selection problem. How do you know which hypothesis space contains only the signal and none of the noise? And this is an open question. This is where it becomes a bit of an art rather than just pure math. Based on what you say, there's a question. Based on what you say, simpler models do not represent noise. And in some sense, yes. Simpler models, however, this has to be taken with a grain of salt. Simpler models can represent the noise, but they don't have the capacity. I mean, the hope is they don't have the capacity to represent both the signal and the noise. And we try to find the learning algorithms are encouraged to fit the signal, so they will be forced to represent only the signal. If the model is too simple and does not fit the data, we call it underfitting. And this is we will, towards the end of the semester, once we have seen enough learning algorithms, we will talk about diagnostics of machine learning, where we try to diagnose overfitting and underfitting empirically. In any case, by the way, I just wanted to mention the difference between regression and classification. In this slide, we are talking about regression. We are predicting real valued numbers. Classification is about predicting a discrete label, where we can have, plus and minus, or spam and not spam, or we can have more than two categories. Anyway, so let me give you so let's talk about linear classifiers. Linear classifiers are, in a geometric sense, they are among the simplest objects that we can work with. So we'll spend some time working on that, working on linear classifiers for a while. So as an example of what a linear classifier might be, suppose we have a toy problem where we want to determine whether a robot arm is defective or not. And for some reason, we are allowed to use only two measurements: how far the arm can reach and the maximum angle it can rotate. The distance, let's call it d, and the angle is a. And let's say that we come up with this linear decision rule. We decide that the arm is defective if 2 times the distance plus 0.01 times the angle is more than the number 7. These are numbers that I just made up. I know nothing about this setting. This is just a toy example. The way we would use such a rule is, let's say for a certain arm, the distance is 3 and the angle is 200 in some scale. Then we see that 2d plus 0.01a is 8, which is more than 7. And so we compute the linear combination of the features. We compare against the threshold. And if it crosses the threshold, we predict a certain label. If it does not cross the threshold, we predict the other label. This is an example of a linear classifier. The features, here d and a, are assigned weights. The weighted features are added up, and the total is compared to a threshold. And if you compare to a threshold, you get it's either true or false. It's defective or not defective, or it's plus or minus. This is an example of a linear classifier. Let's formalize this a bit. In general, let's say we have not 2, but d features. Here, d is the dimensionality. Let's say we have d features together represented by this boldface x. We will, in general, use the notation of boldface lowercase letters to represent vectors. What this means is that we have a collection of d numbers, which I'll call x1, x2, all the way to xd. All of these are together, they form a vector. And those of you who are still not comfortable with vectors, you can think of this as a big array of numbers. All of these are in a d-dimensional vector. So we write this as this x is a vector. So when I'm writing it, I'll try to put an arrow on top, but when it's typeset, it's just a bold-faced letter. X is a vector with d elements, which is in Rd. This is the set of real vectors. The label is for linear classification, for simple binary classification, the label is just two things. Without loss of generality from going ahead, for pretty much most of the rest of the class, we will use -1 and 1 for true and false. Sometimes we'll use 0 and 1, and the context will make it clear. False is either -1 or 0. A linear classifier is also called a linear threshold unit. It classifies an example X using these two sets of parameters, W and B. W is a vector of the same dimensionality as X. So W is also a big array of numbers that looks like W1, W2, all the way to WD. And B is just a single number. B is a real number. The way a linear classifier or a linear threshold unit functions is you take the weights and the example, given an example, you take the weights and the example and you compute the dot product between them. The dot product, we will write this as W transpose X. So remember, the dot product of two vectors gives you a number, which is simply the sum of Wi and Xi. And once you have that, you add the B, which is just a real number, and in the end, you have a certain score. We take a real number, just a number. You take the sign of that number, and that sign is the output. The sign can either be plus or minus. The number is either positive or negative. And without loss of generality, we assume that 0 is plus. So to be more explicit, if W transpose X, or the dot product of W and X, which is just this expression here, if W transpose X plus B is greater than or equal to 0, then you say that the label is plus. If W transpose X plus B is negative, then you predict the label as minus. The term B here is called the bias term. Before we, this is just a formal definition. So are there any questions about this definition? Does this function satisfy the linear property? Yes. Notice that our scoring function here is linear. So everything, so X is the feature, right? So the scoring function is linear in the features, and that's why this is, we call this a linear threshold unit. We have a linear combination of the features, and then we threshold it to get the label. It seems like this is useful only for binary labels because the sign can either be plus or minus. It turns out this is a very subtle point. It may seem, looking at what's on the slide, that this particular strategy is useful only for binary labels, but it turns out that using this building block, we can construct more complicated labels for classifiers. So let's say instead of binary, you have multi-class. Let's say instead of 2 labels, you have 3 labels. You convert that into a binary, a set of 3 binary problems. So let's say you have 3 labels, A, B, and C. You convert A into this is a plus, minus, minus. This is a minus, plus, minus, plus. So you have 3 binary classification problems. So using the tools that we have for binary classification, we can construct more complicated outputs. Essentially, we can encode more complicated things using binary. This is the fundamental point that a lot of computer science is based on. So there are a few more questions. Han asks, what I meant was W times X plus Y plus B is not equal to W times X plus W times B. That's right. It's not linear in that. You should think of it as W times X. So let's say we have a function f of X is W transpose X plus B. Then f of X plus Y is not equal to f of X plus f of Y. But that's just a minor detail. We have a workaround that. The point that we really care about right now is it is linear in the features. It's linear. There's a way to get around that, and we'll see a version of that that'll answer your question, Han. But it's a minor detail that we'll not have to worry about too much. There's another question: what is W again, and do we learn W? W is just a vector of weights. In this example, let me just write this example using the notation that we saw. W is the numbers 2 and 0.01. B is the number 7, or actually, it's in this case, it's -7. And the features X consists of B and A. The goal of learning is to find the parameters of the linear classifier. In other words, the goal of learning is to find this W and this B, given a data set which consists of X and Y. X is an instance, Y is a label. The linear classifier is fully defined using a certain vector W and a number B. Does that answer your question? Let's move on. The nice thing about linear classifiers is that they have a very intuitive and easy geometric explanation, and we can illustrate this in 2 dimensions. Let's say we have these 2 features, x1 and x2, and let's say we have these 2 sets of points, pluses and minuses. We can draw a linear classifier is the sign. This SGN is just the Latin signum function, which is sign. So I'll be using SGN going ahead. The linear classifier is defined by a sign of W1x1 plus W2x2 plus a bias. It looks, if you think about what object this looks like, it's essentially a line. W1x1 plus W2x2 plus B is just a line, and that's why these are called linear classifiers. The separating boundary between well, we'll get there in a minute. So this line W1x1 plus W2x2 plus B equals 0 is a line in 2 dimensions, and W1, W2 here represents a certain direction. In fact, the normal to the line is this vector W1 and W2. The weight vector represents the normal to the line. And the intuitive way of thinking about this is the normal points towards the positive class. And this is the notation that I'll be using going ahead. We have a line and a normal that points to the positive side. We only care about the sign of this thing, W1x1 plus W2x2 plus B. We don't care about the actual value. We only care about the sign. The classification is a sign. In 2 dimensions, we have a line. In 3 dimensions, we can't, of course, plot 3 dimensions in a slide, but you can look around, you see a room, you imagine a certain plane that cuts the room in 3 dimensions. What we get is a plane. If you have more than 3 dimensions, what we call a line in 2D and a plane in 3D is called a hyperplane. A hyperplane is nothing more than a high dimensional generalization of a line. A line cuts so this line here is cutting the plane into 2 parts, into 2 slices, and saying that this side is positive and the other side is negative. Similarly, a plane, you can imagine the plane cutting your room into 2 parts, where we say one side is positive and the other side is negative. In high dimensions, the hyperplane separates the high dimensional space into 2 half spaces. And we say that one half space is positive and the other half space is negative. This is the reason these objects are called linear classifiers is because the decision boundary, the boundary that separates the positive and negative, is a line or a plane, or in general, a hyperplane. So we'll be using the word hyperplane quite a bit. It's just a high dimensional generalization of a line. And for all practical purposes, you can imagine a line in 2 dimensions and call it a hyperplane. Are there any questions about this? While you're thinking of questions, let me kind of expand on this a bit. Remember, we are thinking of binary classification. We want something that separates the space, the feature space of X, which is X1, X2 in this case, into two parts. We could have separated the space into two parts in many, many different ways, but we notice that if we can define a line naturally divides this two-dimensional space in this case into two regions, two half spaces. And the hypothesis space for linear classifiers essentially says, if you have these two half spaces, I'm going to call one side positive and the other side negative. And the goal of learning would be to find this hyperplane that separates the positives and the negatives. Are there any questions? There don't seem to be any questions, so I'll move on. So what we have seen so far is we have seen the formal definition of a linear classifier and a geometric intuition. And now I'm going to talk about notational convenience. What I'm going to talk about next is essentially just something that will make us write less and code less. And as a result, we will have fewer bugs. So notice that remember that the linear classifier is defined in terms of a certain weight vector and a bias. The way we use the weight vector is we just take wi, xi, the sum of them, plus b, and the goal of learning is to learn both the w and the b. Now, first of all, think about what happens if we ignore the b. If you ignore it's easiest to think about what happens if you ignore the b in this picture here. If b equals 0, what we get is we get lines that only go through the origin. This is an example of a line that goes through the origin. This is another example of a line that goes through the origin, and so on. So if we ignore the b, we are only considering lines that go through the origin and nothing else. But that seems like it's a dangerous thing to do, because that means if your plus is here and the minuses are where they are in the slide, sure, there is a line that separates the pluses and the minuses this way that goes through the origin. But what if your pluses were here? There is no line that goes through the origin that separates out the plus and the minus. We have to find a line that does not go through the origin, which means that in the general case, b cannot be 0. So we need the b. We need the bias term so that we have the full space of all possible lines. But the problem is that now we have to keep track of the weights and the bias, and there is a whole group of people who do that. When I say whole group of people, what I mean is there's like certain papers and certain there are like many papers and many tutorials for machine learning where the bias term is always explicitly there. But for the purposes of the next few weeks, I'm going to show you a trick that allows you to pretend that the bias is not there, but always keep it. Suppose I write, so remember my example x is really a big vector of x1, xd, and this is a d-dimensional vector, so I'll put the number d here. Instead of just keeping this d-dimensional vector, what I can do is I can add a 1 at the end to create a d plus 1 dimensional vector. I just add an extra feature, which is always a constant, the number 1, and I'll call it x prime. And similarly, I'll expand w to w prime by stacking all the weights, w1, w2, till wd, all the weights, and just put the bias at the bottom. So I'll call that w prime. I have done nothing here. I have just essentially expanded x by adding a single feature that's always a constant, and expanded the w by putting the bias at the end. Now think about what happens if I take the dot product of this vector and this vector. x1 gets multiplied with w1, x2 gets multiplied with w2, xd gets multiplied with wd, and b gets multiplied with 1. So we essentially get back this summation here, w1x1 plus w2x2 and so on, plus, so x prime, let me write it more clearly, w prime dot x prime is the sum of xi wi plus b, which is exactly the same thing as here. So what that means is that w transpose x plus b, which was this, is exactly the same as w prime transpose x prime, but now I no longer have to worry about the bias term. This is just purely a notational convenience. The bias is there, it's just there because it's inside this thing here. And now the prediction function is the sign of w prime transpose x prime. So what have we done here? We have increased the dimensionality by 1, not a big deal. We usually deal with thousands of dimensions, adding 1 more is not a big deal. We have added a single feature, a constant that is always just 1. Earlier, the classifier was defined by w and b, so we had to learn w and b, but both w and b are inside w prime, so the goal of learning is now just to learn w prime. In the d plus 1 dimensional space, this vector w prime, the line corresponding to that vector, goes through the origin. This is just, as I said, a notational convenience. Nothing has changed in the underlying math. We are just not writing the b anymore. We are just hiding the bias term by adding an extra bias feature. Remember, we always need the bias. So there's a question, isn't this only modeling b as one-dimensional if w prime is in R d plus 1? B is one-dimensional. B is a real number. Remember the way we define it. A linear classifier is defined as a combination of a weight vector, which is a d-dimensional vector. And let me erase all the writing so that there's no confusion. A linear classifier is defined as a combination of a d-dimensional vector and a single real number. A single real number is nothing but just a one-dimensional vector. So B is a one-dimensional vector, and that's why W prime is in R d plus 1. Oh no. Yes. Are there other questions? Now, at this point, many of you are feeling incredibly confused. So there are two ways about it. You can either ask questions now, or you can revisit this and come back with questions on Thursday. This is something that is just, think of this as a warm-up for just thinking about these high dimensional spaces. We'll be thinking about this quite a bit. So it's worth kind of digesting this with the knowledge that we have not changed anything. This is just pure algebra. This is just symbol manipulation. We have not changed anything in the underlying math. It's just a convenient way of writing down this expression as this. And the reason I do this all the time in any code that I write for linear classifiers is because if I do this by adding a constant feature, always 1, I don't have to explicitly worry about W's and B. I can just think about a single vector W, knowing that there's always the bias is always there. This leads to less debugging. This leads to more correct code. And that's why I end up doing this. And it also leads to fewer notational things. And when we are actually looking at learning algorithms, the goal of learning is to learn the W and the B. And unfortunately, which means that we have to iteratively, we will see algorithms that iteratively improve W and B together, which means there'll be an update for the W, there'll be an update for the B, and you might forget to write down that update for the B. But by wrapping the B into the weights, by adding this constant feature, you don't have to forget it, it's there. You get it for free. So I want you to revisit this offline and come back with questions, because I guarantee that at least half the class is feeling that this is confusing, and the other half is feeling that this is so obvious. Why am I laboring the point? Once you see it, it's obvious, and until you see it, it's painful. So if there are no questions, let me now jump ahead to give you an advertisement for a lot of things that we will see in the next several weeks. We'll see a lot of linear classification. We'll see many different algorithms that allow us to learn this prediction function with the weights and the biases. The first one that we'll see is perhaps one of the oldest algorithms for learning a linear classifier, which is the perceptron algorithm. It's an error-driven learning algorithm that updates the hypothesis. In this case, the hypothesis is defined by the weights and the bias. Perceptron updates the hypothesis whenever it encounters an error. But it's still learning a linear classifier. We'll see after we touch upon computational learning theory, we'll see support vector machines, which also learn a linear classifier by framing it as an optimization problem. Once we encounter probabilistic models, we'll see naive Bayes classification. And it turns out that with certain probabilistic assumptions, the naive Bayes classifier is also a linear classifier with a probabilistic interpretation. And then we'll encounter logistic regression, which is another probabilistic classifier, which is also learning a linear model, but it has some similarities to support vector machines in that the learning is actually an optimization problem. So this is not in the next several weeks, but really we will see this maybe, we'll see the beginnings of this maybe even in the next lecture. This will be sometime in the middle of the semester. These two will be in the last third of the semester. So we'll keep visiting this notion of linear classifiers again and again, and we'll encounter different learning strategies for linear classifiers. The nice thing about this is all these algorithms can be generalized to more complex kinds of classifiers. So the learning algorithm is really an interplay between an algorithmic component and the hypothesis space. Linear classifiers present a fantastic hypothesis space for developing algorithms that we can extend to more complex hypothesis spaces. So let me now switch gears very briefly. There are about 8 minutes left, and I'll start something and continue in the next lecture. I'll talk about what are these functions capturing. I can define any class of functions. I can define a function however I want. It doesn't mean that it's interesting. So the next question to think about is, why should we study linear classifiers and what kinds of functions do they express? We've already seen what linear classifiers are. It turns out that linear classifiers express many interesting functions. In terms of the Boolean functions that we've seen, they express conjunctions and disjunctions and m of n functions, but not all functions are linearly separable. Remember, going back to the discussion at the beginning of the lecture, we want to restrict the hypothesis space so that we can represent interesting and plausible functions, but not everything. And we'll see an example of functions that are not linearly. We'll see some examples of functions that are not linearly separable. But it turns out that if you're willing to give up dimensionality, if you're willing to add more features and transform the features into higher dimensional spaces, even these functions that are not linearly separable can be folded into into the class of linear classifiers. So let's start with Boolean functions that linear classifiers can express. Many Boolean functions are linearly separable, not all of them though. And just as a point of comparison, remember that decision trees can represent any Boolean function, and that's one of the reasons why they're great. That's also the reason why they overfit. So let's look at some examples. Conjunctions and disjunctions can be expressed as linear classifiers. Here's a conjunction. What that means is the label y is true if x1 and x2 and x3 are true. Now, this is equivalent to saying the label is 1 whenever the sum of x1 plus x2 plus x3 is greater than or equal to 3. So let's explore how this works. If you want to prove this, the easiest way of doing this, because we have only 3 features, is to write down the entire truth table. We have 3 features, x1, x2, and x3, and I have written down all possible values that they can take. And the conjunction is saying the output is true whenever all of them are true. So only in this place is the output true. Let's consider this quantity here, x1 plus x2 plus x3 minus 3. I've just brought the 3 to the other side. Notice that this summation is negative in all cases except in the last row where it is 0 and the sign of 0 is 1. So this quantity is exactly the same as this quantity. So this is why this is like in some sense a proof that this function here is the same as this function here. We can also bring in negations. The general trick for bringing in negations is whenever you see some term negated, like x3 here, you write down, you pretend that the negation is not there, you write down the conjunction, and then at the last minute, replace that feature with 1 minus that feature. So by pretending that the conjunction is not there, I get x1 plus x2 plus x3 because this is the same. If the conjunction was, if the negation, this symbol here is a not, if that is not there, then you get the same thing as the one on top. So you get x1 plus x2 plus x3, but at the last minute, I replace the x3 with 1 minus x3. And there are a few exercises that I want you to consider. First one, prove that by writing down the truth table just like this, that these two functions, this and this, are equivalent. The next thing I want you to think about, and this is a useful exercise, is what happens if the conjunction was replaced with a disjunction. Instead of an and, what if you had an or? I claim that any disjunction is also linearly separable. So invent a linear threshold function for the case where the conjunction was replaced with a disjunction. Are there any questions? I see there is a question. Is it better to make the features nonlinear and keep the hypothesis space linear versus the other way, where you keep the features linear and make the hypothesis space not linear? There is no free lunch. In both cases, you end up paying the same. You need we will see that the complexity of the model, the complexity of learning is in both cases would be equivalent. So it really boils down to which of these two cases do you have better learning algorithms? Which of these two cases do we have more efficient code, for example? And today the efficient code has gone to the case where the features are linear, but the hypothesis space is not linear because we know how to essentially do efficient optimization for those cases. There's another question. Are there quadratic and cubic models in machine learning? Yes, there are. There are quadratic, cubic, and we can even consider infinite degree polynomials. If you are interested in that, look up the word kernel. Kernels give you an interesting way of getting quadratic, cubic, such models. Or we can just explicitly introduce quadratic and cubic terms, and we will see an example of that. Oh, I guess not today, but at the beginning of the next lecture. Another question is, does this work only for binary features? And when you say this, you mean, what do you mean by this? This idea. So what only works for binary features is the notion of conjunction and disjunction, because these are essentially logical operators which are only defined for booleans. But there are many interesting functions that are linear that are not just defined with binary features. So everything that, remember that a linear classifier does not, the notion of addition and multiplication is not necessarily just for binary features. So linear classifiers are defined for real valued features. It just so happens that binary features can be written as 0 and 1, which are also real numbers. So we can, binary features are part of the real valued features, are contained in real valued features. One other function that I will, this is the last thing I'll do. We looked at M of n functions in the beginning of the semester, and you're also thinking about it in your homework. M of n rules are all linear classifiers. Just to remind you, an M of n rule looks like this. You have many, many features, but you pick a subset of them, a fixed subset of n features, and the label is true if and only if at least m of them are true. Any features that are not in this fixed set are ignored. For example, if you have 5 features, x1, x2, x3, let's say that I pick n features, n equals 3, and I pick these 3 features, and my rule is the label is true if at least 2 of them are true. So it's worth thinking about how this can be written as a linear threshold unit, and the answer is simple. At least 2 of these is really you're counting how many of, by adding them up, you get the number of them that are true. And if the number that's true is at least is greater than or equal to 2, then you get the label to be true. So exactly the same decision rule. All right, we are over time, so I will stop here. And we've had many questions through the class, so I won't stop for questions, but I want you to revisit this and please come with questions at the beginning of Thursday's lecture. And if in case you have any questions, pressing issues that you want to discuss, please come to office hours, which will start in 15 minutes. I'll see you all on Thursday or in my office hours. Bye.